we're going to announce the last homework pretty soon today. It's going to be due exam week, so you'll have plenty of time to work on that problem set. And I am fully prepared as well. I finished all my class notes that I needed to prepare, so I'm prepared for anything that can delay the regular instruction in this period of time. I can record videos, I can have all materials delivered to you in the best way that I can find. All right. We have been talking about observability and controllability. Let's start with a little exercise that's not difficult, but there will be some intuition about this exercise that's going to be helpful for analyzing, as a control engineer, for analyzing system dynamics. So the problem goes as follows. We're going to look at system ABC with systems with ABC matrices that look like this. There are a bunch of ones and zeros in B and C, and the question is whether this is observable or not. So spend a little time to take a look.
The third entry of the first column is 0. So we should just say the other terms in your denominator.
Oh, I see what you're saying. Your concept. Okay, I see what you're saying. What about that then?
Oh, we haven't input to that. No, no, the second one is still the second one is 6 on it. All that can by that third entry.
Yeah. The third, yeah, the third inputs.
Okay, so let's try to do the regular way. Let's construct the observability matrix. Q. So it's a third order system, so we need to do C, CA, and CA square. So it's going to look like 1, 0, 1. Then C times A is going to be first row plus the last row. So it's -2, 0, 0. And then CA square is going to be CA times A. So it's going to be this vector times A again. So it's going to be the first row multiplied by 2, by -2. So we can see that it's not rank 3. So the rank is 2. So therefore it's unobservable. All right. So some of you were looking at, I'll come back to you. Some of you are looking at like, it has certain structures inside, so it actually is possible to directly tell like which of the state is unobservable. So I will get back to that in the next. I would like to talk about, give me any ABC matrix, ABCD matrices. If the system is controllable, I would like to discuss quickly that we can translate the system into controllable canonical form. I will do the same for observable canonical form as well. All right. The problem is actually not so difficult. As long as we know like what we want to see a controllable canonical form, then the result is going to be, the procedure is going to be just some mathematical elaborations. This is what we want. We want that after some similarity transform, the original state, which is ABCD, any ABCD matrices expressed in the system dynamics, then we can translate that into the a new state space where the new ABC matrices, we have discussed how similarity transform manipulates the ABC matrices. So the new A matrix, let's say A tilde, is M inverse AM. So my definition, M is the matrix containing all these columns, M1, M2, and Mn. And then the B matrix, B tilde, is M inverse times B. This is just like doing regular similarity transform. We want, after the transform, B tilde to be in controllable canonical form. So controllable canonical form has a very special structure for B tilde. It's a bunch of zeros, and then in the end is a 1. This is going to immediately give me one column of M. So to see that, you can see that this is, if you multiply both sides by M, then you're going to get B equals M times this special matrix, special vector. So you can see that this is nothing but picking the last column of the M matrix. So immediately you see what is the similarity transform the last column should look like. It should be 0, 0, 0 all the way until the last element. This is solved. So let's take a look at the next one. Let's take a look at the A tilde matrix. So we know this one already. Let's address the remaining. Now we want A tilde to be in controllable canonical form, which has a very specific structure as well. It's a bunch of ones sitting in the off-diagonal elements, and then at the last row it's going to be negative A0, negative A1, negative AN minus 1. We want A tilde to look like this. All right, this is giving us nothing but A tilde is M inverse AM, so M times A tilde should be equal to A times M. If you want to write it out, then the result is going to be very trivial. So it's A times M, written in a column fashion, should be equal to M times A tilde. All right, take a look at this. So this means all the columns of the matrix product on the left-hand side must be equal to all the columns of the matrix product on the right-hand side, column by column. If I take a look at the last column, all right, let's take a look at the last column here. This equals AM1, AM2, all the way to AMN. And then the right-hand side is, let's take a look at the last column. So if I multiply this one to here, the last column of this matrix is 1 times the second to the last plus negative AN minus 1 plus times MN. So it's MN minus 1 minus AN minus 1 MN. All right, this column should be equal to, this is the last column. This should equal to this. In the previous slide, we already figured out Mn, if you think about it, right? So we figured out the last column should be equal to B. So we know this, then this one can be obtained. Mn minus 1, this column can be obtained. All right? Let's do one more time. So the second to the last column on the right-hand side is 1 times Mn minus what? 2, right? So it's the last is from the right-hand side is negative An minus 2 times Mn plus 1 times, counting from here, Mn minus 2. Let's keep track of what we have done. We have figured out Mn, and we have also figured out Mn minus 1 from this equality. All right? From here, so this should be equal to Am n minus 1 here. This is the second to the last column on the left. This should equal to this. We know Mn, we know Mn minus 1, so this is known now. This is also known. So therefore, we can know Mn minus 2. By doing this step by step, iteratively, we can figure out all the previous columns of the M matrix. So if you do that, this is what you can get. So the last column equal to B, this is what we discussed. And then Mn minus 1 should be equal to A times Mn plus An minus 1 times Mn. And then Mn minus 2 should be equal to Am minus 1 plus An minus 2 Mn. All right? So step by step, this is a formula that you can use. So on the left is I minus 1 equal to AMI plus AI minus 1 times Mn. So that's the solution. So we have backwards, we have all the columns in the M matrix now. So therefore, we can obtain how to do the similarity transform. Okay. If you got the basic idea, the situation for observable canonical form is very similar. It's is governed by the fact that we have an idea of how the C matrix should look like after the similarity transform. So it should be in the observable canonical form. So C tilde should be equal to this. And then A tilde should also have a structure in observable canonical form. All right? Just write out similarity transform. This time I'm using R as the transformation matrix. So X equals R inverse X tilde. And then R has the structure of R1, R2, all the way to Rn. All right? To save space, I wrote it in a column notation, but it's the same. So it's R1 transpose and then transpose sign here. We want C tilde or CR inverse to be equal to this row vector. All right? So we want this to equal to CR inverse. In other words, if I multiply things out, I can get C should be equal to 1, 0, 0, etc. times R. So R is the R1, R2, these rows combined together. Therefore, you can see C should be equal to the first row of the R matrix. C should equal to R1. So that's how we can figure out one row of this transformation matrix. So the same for all the remaining rows. So let me write it here. So for these remaining rows, this is because A tilde, we have a specific structure in the observable canonical form. So it's the first column is negative A n minus 1 all the way to negative A 0, and then a bunch of zeros, and then ones, and then a bunch of other zeros. From here, A tilde equals RA R inverse, so therefore R times A should equal to A tilde times R, or written out, R is R1 again, R2 Rn times A should equal to A tilde right here times R all right. The beauty of the observable canonical form, you can see that if you multiply out, because there are so many zeros in these rows, right? Every row is essentially just the two numbers. All the other numbers are 0 for the first n minus 1 rows. And then the last row is even simpler. Just one element is non-zero. We can do the same thing. So let's look at row by row. So the first row is going to give us R1 times A should equal to negative A n minus 1 R1 plus R2. From the previous slide, we already know that given from the previous slide R1 should equal to C, then you can compute out R2, right? I know A, I know all these numbers, R1 is known, then you can get R2. Do the same. R2A should equal to negative A n minus 2 R1 plus R3. After you get R2, put it in here, then you can get R3. Iteratively, you can also have a formula. If you write it out, it's going to look like this. There is a iterative update to obtain all the future rows of the R matrix. All right, so that's the concept. Let's do a practice. Okay, this system is not in a standard controllable observable canonical form, right? Because this is not 1, it's 0.01. So let's transform the system into observable canonical form. These are the formulas, so we can just do it. Follow this recipe. R1 should be the C column, 1, 0, and R2 is R1, 8 plus A n minus 1, R1. So in this example, n equal to 2. right? So R2 is therefore R1A plus A1 times R1. So what is the coefficient here? A is given, so what is A1 in our case here? So A1 are the coefficients of the denominator of the system, right? So that's the, you can get, so let's do the mathematical expression of when we compute the transfer function. So A here, this is the, right? A here is when you have the observable canonical form. A is the one that should be sitting here. So what should it be? We can see here the system, the A matrix looks like that. So the denominator, the poles, the eigenvalues shouldn't change, right? So the two systems, they should have the same eigenvalue. So if I do A minus lambda I, and then the eigenvalue coming out of this should be the same as the eigenvalues coming out of this computation if this is observable canonical form. So for observable canonical form, we already know how if you give ABCD matrices, what is the denominator of the transfer function, which is going to be S squared for this 2 by 2 system plus A1 S plus A0. And then for this one, it's easy enough. Let's see, what should it be? Say that again?
S square minus
S squared minus, so just some computation, right?
S. Sorry.
I should use lambda, but you got the idea. All right, so someone is saying you have some numbers. It's going to be quick and easy. 1 minus lambda, negative lambda, 0.01 determinant. So it's going to be multiply out. I would think I can get this minus 0.01. What do you think? Right? So this is what I got. Then I can see A1 is negative 1. So therefore, this should be R1A minus R1. Then R1A is the first row of the A matrix. So it's this one minus R1. So this is what I would get.
Is that determinant wrong where you get the 0.01? Because don't you do like the diagonal and then when you go to the other diagonal it's 0?
This one?
Yeah. Should be 0.
Yeah. That's a typo. Okay. Fortunately, it doesn't impact A1. All right, so I used to do this. Students pointing out a typo in class, I would give him some extra credit. But I don't think you guys need that kind of a motivation. So cool. I think we are in a relatively good shape. All right. What I would like to do next is to show you that the computation in MATLAB. So our A matrix is 1.01 and then 0, 0. C is 1, 0. Let me see if I can make it large. Cool. We got R1 is R1. It's C actually, right? So R1 is C. And then R2 is 0.01. So our matrix should therefore be R1 first row, R2 second row. And so let's see the formulas for after the similarity transform. If you take a look at the notes that you just did, it depends on R and the inverse matrix of R. A tilde should be R times A, I got A, and then times inverse of R, right? So you can see already A tilde is on the top right is 1 instead of 0.01. And then C tilde, I wouldn't be surprised, C tilde would be C times R inverse, and this 1, 0. So therefore we have transformed the observable system into observable canonical form. All right? The procedure is built for like MATLAB computer programs to do these kind of transformations. It's very systematic.